Now we have discussed a lot of basic laws and basic circuit analysis techniques, right? All of this we will now see for AC circuits as well. There's not going to be much difference. We will be making use of impedances in place of resistors, and we will be using the phasors instead of the actual DC values. We'll discuss them one by one, then it will become clear to you. So the Kirchhoffs laws, they will remain the same as it is. For example, if you take KCL, there is one node, let us say, and various currents are flowing. Now the currents are in phasor form, right? So this is I3 bar and this is I4 bar, let us say. Then what will be the KCL here? I1 bar plus I2 bar plus I4 bar. These are all entering the node, which is equal to currents leaving the node, I3 bar. Okay. So just that we are making use of phasors here, nothing else. Similarly, we can say the same thing about KVL, right? So there is a circuit element here, let us say. We have 3 circuit elements. Now each of the voltages we will take the phasor form. So this is V2 and here we can take as V3 bar. Then if you apply the KVL in counterclockwise sense, okay, so then what you will get the equation? If you start from V1 bar, first negative polarity is coming, so minus V1 plus V3 bar is going to be positive minus V2 bar. This is equal to 0. So we have applied the KVL for this loop. So you can see that this is just like normal KCL and KVL, just that we are using the phasor form. Nothing else is different. Okay. Next we will see the impedance combinations. So this also, it will be just like resistors only. If there is a series combination, this means that the current through each of the impedance element will be same. So impedance will have both the resistive and the reactive elements. So let us take this to be Z1, Z2 and so on till Zn. Then what will be the equivalent, Z equivalent? This will be the sum of all of the impedances. So this is for the series connection. And what if all of the impedances are equal? If Z1 is equal to Z2 is equal to so on till Zn. This implies that Z equivalent is equal to N times Z. Okay. Now we will see the parallel connection. In parallel connection, what will be same? The voltage will be same. So using the same derivation that we used for resistors, we will get the expression. Here we will take as Z1, Z2 and so on till Zn. Then what will be the equivalent? The reciprocal of the impedance, equivalent impedance will be equal to the sum of the reciprocals of each of the impedances. Okay. So now remember this Z1, Z2 and Zn, these are all, they are not phasors, but they will have a real and imaginary part, or in other words, they are complex numbers. And you can also represent them in the magnitude and phase form. Now one thing that you can see here is the reciprocal of the impedance will be what? It will be simply the admittance, right? So Y equivalent, that means the equivalent admittance will be equal to 1 by Z1 is again the admittance of this element, the first element. So you can write Y1. Similarly 1 by Z2 is Y2 and so on till Yn. So when complex impedances, they are in parallel, you can add their admittances. Okay. It is easier to deal with admittances for a parallel combination. Now what about if there are only two impedances in parallel? If only Z1 and Z2 are in parallel, then what will be the equivalent impedance? Just like the case of resistance, the product of the impedances divided by Z1 plus Z2. Okay. And finally, if all of the impedances, they are equal, let this be equal to Z, then what will be the equivalent impedance? This is going to be Z by N. We'll now do a problem so that it will become more clear to you. So here the question is, find input impedance for circuit operating at 50 radian per second. So this is the circuit. Now these are the open circuit terminals that are given. So we have to look through these terminals and find out the input impedance. So we'll take this as Zin. Okay. So what will be the solution here? If you can see here, this is in ohms, the resistances are in ohms, but the capacitor and inductor, they are not in ohms, so we have to first find out their reactance. So let us take this 2 millifarad as x1 reactance, 10 millifarad as x2 and 0.2 Henry as x3. Okay. So then what will be x1? This will be 1 by J times omega is given as 50 radian per second, right? So J into 50 into 2 into 10 to the power minus 3. So here you are going to get minus J10. Similarly, you can find out x2 as minus J by 50 into 10 to the power minus 3. So this you are going to get minus J2 ohms. What about x3? This is J times omega 50 into L, 0.2. So this you are going to get J10 ohms. Now how will you find the input impedance? So you can see that x3 is in series with 8 and 3 ohms is in series with x2. Now these both are in parallel, which is again in series with x1. So first we will write the expression Z input is equal to x1 plus, if you take this as one combination, if you take, let us take this to be Z1. And this entire combination we will take as Z2. Okay. So then what will be here? X1 plus Z1 parallel to Z2. Okay. So first we can find out Z1, then we can find Z2. So what will be Z1? This is equal to 3 plus X2. X2 is minus J2. What is Z2? This is equal to 8 plus J10, right? 8 plus X3, which is J10. So now what will be Z1 parallel to Z2? Z1 into Z2 divided by Z1 plus Z2. Z1 plus Z2 you can write directly. This is going to be 11 plus J8. Okay. Now here it is easier if you can keep the magnitude form. The final answer you are going to get 3.39 angle minus 18.37 degrees. Okay. So from here you can substitute in this and you are going to get Z input is equal to x1 is minus J10 plus 3.39 angle minus 18.37 degrees. This again you have to write in rectangular form. How will you write? 3.39 cos of minus 18.37 plus J 3.39 sine minus 18.37. The final answer you are going to get 3.217 minus J 11.068. Next we will discuss voltage division. So here also it is just like in the case of resistances only, just that in place of resistor there is going to be impedances. Okay. So where voltage division will come into picture when there are a number of circuit elements in series. Okay. And if the total voltage across the combination is given as V, then what will be the voltage across each of the elements? That is what voltage division will give, right? So these are all phasors. So don't forget to keep the bar. Okay. So what will be voltage V1? This will be equal to, so the impedance also we have to take, right? So let this be Z1, Z2 and so on till Zn. So V1 bar will be equal to Z1 divided by the sum of all the impedances into the total voltage V bar. This is for the first impedance. Now if you take any, in general any impedance if you take, okay. So that means voltage across Zk. What will it be? Vk bar is equal to that impedance Zk divided by sum of all the impedances into the total voltage. Now what if all of the impedances were equal? If all impedances are equal, let us say, so on till Zn, which is equal to Z, then equal voltage distribution you can see. Okay. So that means V1 bar is equal to V2 bar is so on equal to Vn bar, which is equal to the total voltage divided by the number of impedances in series. Okay. So this is one expression that you need to remember. This is another expression. This is voltage division. Then what about current division? In current division, we will be dealing with impedances in parallel and how the current will be divided, right? So that means, let us say this is Z1, Z2 and so on till Zn. And the total current flowing through this is I. So this is I1, I2 and so on till In. Then what will be the current through the kth impedance? So that means Zk, what will it be? This you can write as Ik is equal to 1 by impedance divided by the sum of reciprocals of all of the impedances into the total current. So these are all phasors. Don't forget to keep the bar. Here also Ik bar. Now what is the reciprocal of impedance? It is nothing but the admittance. Okay, so you can also write as Ik bar is equal to the admittance divided by sum of all the admittances till Yn into the current phasor, total current phasor. Okay, so this is the current through the kth element. Now what if all of the impedances are equal? If Z1 is equal to Z2 so on till Zn, this is equal to Z, let us say, then the currents will be divided equally. So that means I1 bar is equal to I2 bar is equal to so on till In bar, and what will be this value in terms of the total current? I bar divided by N is the total number of impedances that are present in parallel. Okay, and finally when only two impedances are present, if only two impedances are present, then what will be the current division? Then I1 bar is equal to the other impedance Z2 divided by Z1 plus Z2 into I bar, and I2 bar is equal to Z1 divided by Z1 plus Z2 into I bar. Now we will do a small problem. Find the current I of t. So this is a circuit given. I of t is the current through this capacitor. Okay. So the total current is 2 cos 2t and we have two branches in parallel. Okay. So what we can do here, we will take this branch as Z1 and this branch as Z2. Okay. So now what we have to find? We have to find the current through the second branch. So you can pause the video and you can solve yourself first. So I of t we will represent as I bar. Okay, because we are dealing with the phasors. And what will be the source current? We need the phasor, right? So let source current be Is, which is equal to 2 angle 0 degrees. So then what will be I bar? This will be equal to the opposite impedance divided by Z1 plus Z2 into the total current. So Z1 is given by 5 plus J10 divided by 5 plus J10 minus J25 into 2 angle 0 degrees. This, if you simplify, you are going to get root 2 angle 135 degrees. Now this is the phasor form we need in the sinusoidal form. Okay, so we have to convert back into sinusoidal form. So I of t is equal to the maximum amplitude is given by root 2, and here we use cos because here the reference phasor has cos 2t. Okay, so cos 2t plus 135 degrees. So this is the expression for current through the second branch. Now the next technique is Wheatstone bridge. So here we had the resistor combination like this. Okay, and the current through a resistor which is joining these 2 points, this is called as the bridge. Okay, and the current through this will be 0 if the condition R1 by R2 is equal to R3 by R4, right? So if this condition is satisfied, then the current through the bridge is going to be 0. That is the Wheatstone bridge. This condition you can also write as R1, R4 is equal to R2, R3. So that means the opposite resistors. Okay, so they can be multiplied and their product will be equal. Now the same thing can be applied for impedances. Okay, so that means instead of resistors, there are now impedances. Here also it is the same thing only, just that the impedance will have magnitude as well as phase. Okay. So let us see, this is the bridge and the current through this is I. Okay. So we will take this as Z1, Z2, Z3 and Z4. Now the condition for balanced bridge is, condition for balanced bridge means that the current I through the bridge is 0. So what will this be? The opposite impedances, the product of opposite impedances will be equal. Okay. So this means that if you write in the magnitude phase form, then you're going to get mod Z1 angle theta 1, mod Z4 angle theta 4 is equal to mod Z2 angle theta 2 into mod Z3 angle theta 3. Okay. So this means what? If you take the magnitude condition, then you will get the product of the magnitudes is equal to 0. Product of opposite magnitudes. Okay. And the phases will be added, right? Angle theta 1 plus angle theta 4 is equal to angle theta 2 plus angle theta 3. So this is the magnitude condition and the second one is the phase condition. Next we will see how to do the nodal analysis. We will make use of an example. So the question here is to find V1 bar and V2 bar. So V1 and V2 are given here. Okay. And this is the circuit. So now we will try to solve this using the nodal analysis. Okay. So now you can see here how many nodes are present. First we have to identify, right? So there are only 2 non-reference nodes. This is the reference node. And one more thing that you can see here is across the 2 non-reference nodes there is a voltage source. Then what we have to do? We have to form a super node. So this is a super node question. Okay. So we'll try to solve this now. The very first equation that you can write is V1 minus V2 is equal to 10 angle 45 degrees. Okay. Why we are taking V1 minus V2? Because plus positive polarity is towards V1. Okay. So the first equation is V1 minus V2 is equal to 10 angle 45 degrees. Next we have to apply KCL at super node. Okay. So that means what? You have to consider this entire, both of the nodes we'll have to consider as one single node and we have to accordingly apply the KCL. Okay. So then what are this 3 angle 0 current is entering the super node. So it will be, we'll take it as positive. Now all of the currents we will take, all of the other currents we will take it as leaving. So that means 3 is entering. So 3 angle 0 degrees is equal to the current leaving this node, leaving through this J6 and through this 12 ohm. Okay. So what you're going to get through minus J3 ohms, it will be V1 minus 0 divided by minus J3. The current through J6 ohms is V2 minus 0 by J6 plus once again through 12 ohm also it will be the same. This if you solve you are going to get J4 V1 plus 1 minus J2 V2 is equal to 36. This is the second equation. So now we have 2 equations and we have 2 variables V1 and V2. So we can solve using the matrix form. So what was the matrix form? We will first write in the matrix form, right? So this is going to be 1 minus 1 J4 1 minus J2 into V1 V2. This is going to be what? 10 angle 45 degrees and 36. So using the Cramer's rule you can now find V1 and V2. How you can find? V1 is equal to delta 1 by delta. What is delta 1 here? First we will write delta, then we will write delta 1. So delta is going to be this determinant of the coefficient matrix. So you're going to get 1 minus 1 J4 1 minus J2. Okay, and delta 1 is the first column you have to replace with this, okay, constant matrix. This is going to be 10 angle 45 degrees, 36, and the rest of it remains as it is. Now how will you find the determinant? The rest of it is going to be the same only, 10 angle 45 degrees into 1 minus J2 minus of 36 into minus 1 divided by 1 into 1 minus J2 minus 1 into J4. So if you simplify this, the final answer you're going to get is 25.8 angle minus 70.53 degrees. Similarly, you can find V2. V2 is going to be what? Delta 2 by delta. Okay. So this is equal to here 1 J4 and here 10 angle 45 degrees. Second column is being replaced. Okay. And delta will remain as it is. 1 minus 4 J4 1 minus J2. Okay. So if you solve this, you're going to get 31.405 angle minus 81.18 degrees. So you can see that the procedure is the same, just that instead of dealing with the DC values, we are going to deal with the phasor values. Okay. Next we will do the mesh analysis. So this also will make use of our question. So the question is, write equations to apply mesh analysis. That means we'll only have to write the equations. We don't have to solve it. Okay. So how many meshes are here? This is one mesh, this is second, third and fourth, right? And you can observe one more thing, that there is a mesh that is being associated with two meshes. So this is a super mesh problem. Okay, so we have to write the equations accordingly. So first what we will do, we will take this as mesh 1. So we have assigned the current I1. This as mesh 2. So we will take the mesh current as I2. This current we will take as I3. This current we will take as I4. Okay. So the KVL for mesh 1 and 2 will be straightforward. No problem there, right? So what will be the KVL for mesh 1? 10 angle 0 degrees is equal to 8 minus J2 into I1 minus 8 times I3 minus J2 times I2. What we did? The sum of both the impedances through which I1 is flowing into I1. Now through each of these impedances, another current is also flowing. Through 8 ohms, I3 is flowing, which is opposite to I1. So minus I3, 8I3. Similarly, I1 is flowing like this, I2 is in the opposite direction. So minus of minus J2, I2. So this is the equation for mesh 1. Now for mesh 2, what will be the equation? Here you can see that 3 angle 0 degrees, there is a current source which is associated only with the second mesh. So that means that mesh current we can directly write as, but you have to take care of the direction. I2 is flowing like this, the current source is giving current in the opposite direction. So what will be the value of I2? It will be minus 3 angle 0 degrees. Okay. Next finally, super mesh equation. In super mesh, what we have to take, we have to consider both of the meshes together. So that means like this. So what will you get here? First, this 8 ohms and minus J4 I3 is flowing. So you can write 8 minus J4 I3 plus through 6 and J5 I4 is flowing, right? So 6 plus J5 I4. Now through 8 ohms I1 is also flowing in the opposite direction. So minus 8 I1. Through J5 I2 is flowing. So minus J5 I2. So this is equal to 0. This is the third equation. What is the final equation? The equation applied through this current source. Okay. So you can see that I4 is in the direction of the current source. So you can write I4 minus I3 is equal to 4 angle 0 degrees. So this is the fourth equation. So now you have 4 equations and 4 variables, or you can say 3 equations and 3 variables. Why? Because I2 is already known here. Okay. Now source transformation. So here also it is going to be the same thing only that we are going to use phasors here. Okay. So we have a voltage source in series with impedance. So let this be Vs and this be Z. Then if you want to convert into a current source in parallel with the same impedance. Okay. So impedance will not change. The current value, however, what will it be? Is is equal to Vs by Z. Here you can draw the alternating current symbol. Okay. So this is when you convert from the voltage source to the current source. What about if you want to get the other way round? So in that case, what will be the value of Vs? This will be equal to Is into Z.